No. Remember, again, I'm from Colorado. You know what the Colorado state slogan is?
Actually, do have guns laying around on
Yeah, I know. That's that's right. That's right. And in their cars, and
2 or 3 on them.
yeah. Anyway, science. Basically, it's saying it's a set of accepted facts theories that explain the facts. Pretty much, really, it's why does this really work the way it does, or why does this occur the way it does, versus what we could kind of postulate, ponder. It's like, what is it? Why? Why is this happening? You know, whatever is being done by the institution carrying on scientific activity, to a particular approach to a method. Popular fictions. The goal is obviously to accumulate facts. Usually it's trying to, sometimes it's not always what science tries to prove, it's what it's trying to disprove. Science distorts reality and can't do justice to fulfillment of the human experience. Again, science versus existentialism. If you guys want to talk philosophy one day, that's great. Just save it till after the program. Scientific knowledge is truth. What do you guys think about that?
I think it's pretty
It changes.
It's always changing. Like, you know,
What
this is
science
not,
truth was
it's
even
not
10
set in
years ago
stone.
isn't now.
Yeah, we don't get the full picture, or we only get part of the picture, or you know, the case may be. Science is concerned primarily with solving practical problems and social problems? No, not even at all. So again, science is neither a philosophy nor a belief system. It is a combination of mental operations that has become increasingly habit of educated people and culture of illuminations hit upon by a fortunate turn of history that yield the most effective way of learning about the real world we ever conceived. You guys get all that? Okay, I'll let you guys read it later. So, why do we see what we do and not some things? You know, why is this occurring, this and this doesn't, you know? A little paleontology for people.
I didn't even know what that was.
You can't you see a little bull and little horses?
No, now, but no. There's a
Explanation, prediction. You know, obviously, you know, what's the explanation? If we see a bunch of people come walking in this class about 6 o'clock, why are they here? Why do they keep doing this? And the prediction is, you know, well, is this going to be a repeating pattern? That's all we're trying to look for. Why are these things occurring? Mythos, the word, authoritative account of facts that is not to be questioned. Again, like I said, I guess we're getting more of ancient history here. Antiquity. Age of antiquity? Does that qualify? Yeah. So, don't question the gods or your paramedic instructor. So anyway, Miletus, father of Greek science, philosophy is capable. You know, man is capable of understanding nature. Nature is a phenomenon that has explanations. Obviously, knows the Greeks. You know, there's a lot of pondering. You know, I don't know what to say about pondering, but there's a lot of curiosity of why the world is the way it is. You know, we have certain one of the places where we start seeing schools of medicine pop up. You know, architecture, and so forth. Logos, the word, and account for the facts whose truth cannot be demonstrated or debated. And obviously I think it comes into logic, develops into logic. Advocated deductive reasoning as a tool for understand, logic and, rationale, because understand these are all tools. And especially when you get out there, you're going to see a lot of things that are not logical and rational. Just remember that. They're just tools to try to get us to an end. Anyway, you might be familiar with the term of deductive reasoning. From the general to specific. If all men are mortal, and Socrates is a man, therefore Socrates is mortal. Pretty much we're saying 1 + 2 = 3. Any questions? Yeah. Big thing with deductive reasoning, both premises have to be correct. They have to be factual or whatever the case may be. So, again, the conclusion is only as good as the premise. And keep in mind, it goes from general to the specific. and it doesn't really generate anything new because we're already dealing with what is present at this time. Problem with Aristotle. Well, one, he liked to beat himself. I think he spent too much time with Plato. Sorry. It's late. I'm getting a little... Huh?
I played with Plato when I was a kid.
So Aristotle, like I said, he didn't... just stop. Just stop where you guys are going. I know where this stop. Just stop. Okay, understand Aristotle, again, didn't experiments or observations to check the validity of what he did, okay? Pure rationalist, thinking is good enough at that point. Francis Bacon, on the other hand, if you wonder how the world works, begin with the facts, not the prejudice about facts. So we're getting something a little bit more refined at this point. Again, we're going to, infer general instances to specific observations and draw conclusions about the future past and so forth. Basically, with induction, now we kind of go the reverse direction of, we're going to go from specific to the general. There we can kind of sit there and say, well, maybe we can kind of create or discover. Actually, the thing is, if you kind of think about it, we really don't create knowledge. We more or less discover it. So... And the accuracy of the knowledge can never be proven with 100% certainty. So, and again, it's observations. The observations have to be 100% consistent to get the 100% result. Galileo, on the other hand, well, if we have a theory, let's test it. Let's see if it comes out. So, and during the experiment, try to control all variables you're interested in. And what's a variable?
Everything.
Yeah. One thing that I've seen a couple of people that had really, really strong science backgrounds come through here. And it was actually very confusing for them because science, if you guys go through science programs, they always do things that are referred to as in vitro. You guys familiar with that term? Yes, no? Science, they try to create the most sterile, perfect environment. So we're trying to isolate one event to the next, or what it is we're trying to do. You put medicine in, that goes out we throw that out because now we're talking about practical application of a concept. For example, if you guys taking a physiology class, they might talk about, well, this is how the kidneys work, this, and here's the osmolarity. Well, if you've been in medicine, it's like, well, you don't understand that osmolarity can be altered here, 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 and here, or this can change here, here. Like I said, to them, it's pure in vitro. It's try to get down to most purest working. Medicine, we start seeing all those other little variables that come in and say, but we know those are there. Science, pure science isn't really concerned about that. You guys with me on that? So if you ever start talking to science majors and they start kind of getting you like, well, wait a minute, there's that's where that translation gap is.
So that's mostly because they're trying to teach, like you're talking about the kidney stuff. Like if under perfect circumstances, it's kind of hard. Well, if you don't know anything about the kidneys, well, this could happen, but this could happen. Now you're like, okay, so how's the kidney work?
But the kidney doesn't function like that.
Right. I get if the world was perfect and
the perfect isolated.
This is how it would work. Later on you'll learn about.
It's almost actually going back to in its own kind of strange sort of way of Socrates. You guys, anybody read anything about Socrates at all? You talk about Socrates in the forms. The perfect form was the perfect dog. The perfect thing. Then everything gets branched out. That's almost kind of what they're trying to looking at. What if the perfect kidney or whatever the perfect heart is going to have this much of an ejection fraction? It's going to have this much muscle tissue per se. Versus we're looking at like, no, actually no. There's going to be consistent variables. They're not really concerned about those consistent variables. They're looking at that pure form. So now, of course, you got Isaac Newton's mathematics is the language of nature. So, world observation can be encoded in mathematical form. I think you probably see a lot. We're going to see a lot of that. I think you see a lot. We're going to be playing with a lot of equations, especially just when it comes to actual body functions. Like, you guys know what the equation for cardiac output? Stroke volume times
contraction force or something like that.
Mm-hmm.
Contraction force.
Yeah. Stroke volume times rate. That's all it is. How much blood are we squeezing out? How fast are we doing it? Okay, sounds like a good concept. We're going to play with that concept. How does that concept get useful? Okay, well, if I'm kicking out so many liters of blood, now I got to worry about peripheral resistance. How much peripheral resistance? We calculate that. We calculate blood pressure. Okay, now we're going to play a fun game. We have, okay, let's say you're a child. Your stroke volume is pretty much almost not there. You rely on heart rate to compensate. So we just took a piece out of the equation. Now see how we got that cascading effect? Now we got to worry about the actual peripheral resistance, because that heart may not be able to push hard and fast enough to create that. So how do we start altering these things to get back to a norm?
Go from like 80 to 140.
Yeah. pH. pH. Acidity.
Well, I mean, I know what it is, but
Yeah.
how
Yeah, it's an inverse relationship to hydrogen. It's now I can't. I'm seeing the equation. I can't. Was it the lower? See, the lower the hydrogen ions, the higher the pH. Yeah, inverse relationship. Does that make sense? So that's how a lot of this applies to us. Same thing with medications, especially when you start doing weight-specific medications. We're always trying to get that therapeutic threshold. So anyway, with the scientific observation, starts with an observation. After that, we make a hypothesis. What's a hypothesis? Best guess. So, see the paramedic student walks out of the room crying. Why does he do that? Hypothesis? I think he failed the test. Okay. Okay, what if he does it every day? Okay, so let's do an experiment. How are we going to experiment the paramedic? How are we going to recreate a paramedic student that's going to walk out the room crying? So we got to find a paramedic student.
Pick your subject.
Yeah, we got to put the paramedic student here, and we got to create an event that will make him cry and leave the room. So there's our experiment. Then we watch our observations. Did it work? Did we recreate this? And obviously, if it works, then we can call it an empirical law. So we put the paramedic student down. We sit him down. We put this stimulus called a test before him. He leaves. He gets up and cries. Therefore, if we give paramedic students tests, we can say it's empirically that they're going to walk out crying. I think that's pretty reasonable, right? So, and again, they're about kinds of events, not a single event. So obviously what we're doing, that it's not a single event, we're dealing with a kind of event. Because a paramedic student can walk in, not take a test, and walk out and just run home and think, hey, life is great. So, and then we're trying to show a relationship between two or more events. Okay, the event, walking in, walking out crying. And it's supported by a large amount of experimental data. How many paramedic students do we need to get in here to start taking these tests to see if we really get the same thing out over and over? Are we actually going to have 100%? Was it the variable, as I always say, is plus or minus? Was it 0.5 or something like that in statistics? And if you get like to a higher point, then it actually becomes invalid. So. And hopefully this will be applicable to every situation. Therefore, we know, well, maybe we won't tell the paramedic it's a test. We'll call it a quiz. And maybe they won't leave crying. I don't know. Another example is, what they're talking about here is like Boyle's Law. You guys familiar with Boyle's Law? divers? You dive. So you're familiar with Boyle's Law and all that business? Yeah. So pressure changes on the volume of gas. What happens when you start going deeper in the water? More pressure. Okay. So why can't you just come straight up?
Expands.
Expands too fast, you don't get enough.
Oh, you get a lot more than if you go. No, if you go too fast, you're not getting the bend.
Get too much nitrogen?
Nitrogen. What happens is that when
There's the mix.
deeper, that nitrogen can become small enough it can actually move out of the bloodstream and into the tissues. Then when we go back up, that nitrogen expands into the tissues, and that's what they call the bends. The other flip side is, like they said, they'll tell you to keep breathing and exhaling as you're going up, because that oxygen was compressed in the deep, and then it starts expanding. You go too fast and you hold your breath. Guess what's going to happen? Pop. You know. Now you've got a lack of lung problem. So. Huh?
I said you're not going to care because you're not going to be alive anyway.
So again, like so, he showed that the results showed that as the pressure increased, the volume decreased. More pressure, volume goes down. So pressure volume equals a constant. So if we manipulate the containers, make it bigger, smaller, so forth. Now, Gay-Lussac said, well, what if we add temperature? What does temperature do? That can make things more active, or it can make things, obviously, what happens if water gets cold, what happens? Raises. Water gets really hot, what happens? Huh? Evaporates. So, again, we saw some similar properties again with, temperature can, was it the actual, the activity of the molecules bouncing around off each other? I think it was put. So, and again, we start adding pressure, temperature, and volumes. Now we've got 3 different things we need to work at. Again, with that diver going into that cold water, we got to deal with. So it's not just one problem. It just explains how it works. In other words, it's saying, it's nothing personal. You go down, obviously more pressure, increased volume, you come up, we're going to get the opposite change. Kind of like we, say air goes in and out, blood goes round and round. We start changing those 2 principles, we start seeing different effects. It's just the way it works. We need a theory. It means of relating laws, describing a class of events to a framework, a set of principles described in terms of differing those used from other laws. Anybody want to give me an English translation on this? Huh?
I thought I had it written down somewhere.
What's a theory?
It's an educated guess of
Yeah,
what something's going to do or how it's going to work.
Yeah.
Or what your outcome is going to be.
This is how I think it works.
We've already got these set of principles here. We already got this stuff established, so in theory, all this should work. Right? Because we've already discovered all these things. So we're sitting there saying, we get this piece, in this piece, it should interact and create this. Does it always? No. But in theory, it should work. So again, observations predicted. Again, going back to the gas laws here, by ideal gas laws are explained by the theory of kinetic gases, movement of gases. So let's say assume that the molecules are like gases, like little, billiard balls. Wouldn't that make the gas pressure equivalent to the impact of balls inside the container? Let me ask you that. Let's say we got all these little pool table. If we increase the pressure, what's going to happen to those balls?
Crush.
They're getting closer, right?
Yeah.
What if we increase the temperature? They're going to start moving farther. So we got a little bit of change there. So if we decrease the container, what happens to the size of the impact? What happens if we to the number of collisions if we increase the velocity? What's velocity? Speed. What's the equation for force? Mass times mass times acceleration. That's force. So we've increased the force at that point. So you guys catching the gist of this? So a theory is good if it is accurate, consistent, broad, simple, and fruitful. Keep an eye on that for later down the road. Why are there no scientific truths? Obviously the problem of induction. Hypothesis laws are products of inductive reasoning. And what's inductive reasoning? Something general. Just say it again.
It's from specific to general.
Yeah. So products of inductive reason are only as good as the next observation. So we start adding in more observations. Obviously, we come to we're discovering new truths that are influencing what's going on. That's all we're really coming down to. So no amount of data will ever confirm a hypothesis, law, or theory, but it takes place of a negative data to refute it. So again, the thing is we're discovering new principles, laws, and everything as we're kind of going along here. Falsifiability is science characterizes the tendency to suspend beliefs until evidence of an appropriate kind is produced, and then to believe the proposition in question to a degree that the available evidence warrants it, without inclusion of possibility of further confirmation. Keep an eye out on this one. This is just one of those, be familiar with the term. So in other words, we're not going to believe it until we've actually got some kind of proof behind it, but definitely be familiar with this term.
Like be able to recite it word for word.
And for you, yes. That's going to be your special essay question. Well, one of your special essay questions.
Oh, shit.
I thought you were going like, yes. I was like, damn.
No.
Usually we get a little bit, know each other, but then we start throwing each other. Well, you already threw her under the bus. So.
Yeah, you did.
So norms of science, ideally, we're trying to actually understand, we're trying to be very impartial and skeptical. We're trying to get rid of that personal bias. It's got to be universal, constantly, happen and, should always be occurring. And again, like I said, there's the issue of originality and accessibility. Like I said, we want, you guys remember probably about 10 years ago, supposedly they came out and they cloned a human out in France, but nobody ever had the accessibility to it. Nobody had any data to it. That kind of goes with those kind of concepts right there. But we can clone a lamb, though, or sheep, rather. Does that make you happy, Ethan?
I saw it on TV.
Okay. Anyway, hallmarks of pseudoscience: seeking mysteries and recursive thinking, appeals to myths, casual approach to evidence. Again, it's kind of like I said, science is, we just know what it is, what it does. We don't want to put, is it really working this way? If not, how do we isolate it? Now we're actually trying to take away a lot of this kind of comes down to is more of a personal approach or personal bias or feeling, however you want to put it. Explanation by scenario. Yeah, it's what's anecdotal? It's anecdotal evidence. We do this all the time, believe it or not.
That's just the way we've heard it, and that's just the way it is.
Yeah, or you sit there, like actually one of the best recent ones I heard was I was talking to a guy I know, and he was sitting there saying, yeah, you understand I could tell you about the last 100 patients I ran, they all had insurance. Well, how do you know that? Did you actually see it? Did you actually do it? No, I'm just, but that was that anecdotal, I came to that conclusion, but I don't have anything to really support it. That's actually, believe it or not, a lot of EMS science in its makings. So
a conclusion with no support, basically?
It's a very loose observation. Like I'll come up with anecdotal evidence, with students because I see patterns, but I don't have data to back up those patterns and say, yes, this is what I've noticed, or these are things I've seen. It's just, I just seen this across the board, and I'm comfortable saying
But
it.
just making an ignorant judgment, pretty much.
Yeah, it's a pretty broad guess. Yeah, but I got, like I said, pretty ignorant at times. So scientific language does not make science, but it does make Star Trek. Bold statements don't make it true. Be careful of people. They really, this is careful of the whole language and bold statements, especially with dealing, there's some interesting characters out there in EMS that they know how to talk the language and they know how to come off very authoritative, but they aren't knowing what It's just really kind of more upfront because they really don't know what they're doing. So hearsay does not equal correctness. If you want to, I always love this. Well, I read the research and it said this, and I'm like, okay, where's the research? Where can I get it? Well, I just read it and it said this. Well, I want to see this. Well, you understand, it's like, I don't want to deal with it then. So, rumors do not equal reality. I'd actually kind of disagree. In the scientific world, yes. That is true. In the scientific world, that is true. A perception of people, that is. Just remember the difference in that. The unexplained is not inexplicable, of course. Correlation does not mean causation. Okay, we can go with that. Okay. Coincidence does not mean connection. Again, like I said, obviously, the thing is, we need to have some kind of substantial data to back this up, saying this is really why it's working. So, well, I'm going to stop here, guys, and we'll pick this up tomorrow, or Tuesday, rather.
This is the last slide.
Oh, is it?
Mm-hmm.
Oh, never mind then.